So I'm going to go over real quick why it is that Peano arithmetic is ultimately the problem with behind the incompleteness theorems, right? So in both the first and second incompleteness theorem, what Gödel is looking at is systems that incorporate Peano arithmetic, right? Now we have probably going to misspell this. We have Presburger arithmetic, which comes about, I think, in 1928. Peano arithmetic in the late 1800s, 1880s, something like that. Okay, so this includes addition and multiplication. Presburger arithmetic comes along specifically to avoid the sorts of problems that Gödel's incompleteness theorems demonstrate are unavoidable when you have Peano arithmetic. So Presburger arithmetic only has addition. So why? What is happening here? It's actually really simple. It's very, very easy to see. If you look at Peano's axioms, you get the successor function is extremely, extremely important. Okay, now, what is the successor function doing? The successor function is saying, to get the successor, I'm going to paraphrase, to get this successor to a number, just add 1. Okay, but there's some caveats. Now, 0 is not the successor to anything, and then an implicit 1, which is not in there, but it really, really should be, is, so you get this. This one is in there, and I'm going to write it my way. Alright, or the successor to 0 is 1. Okay. Now, in order to actually demonstrate how this extends, you need this. You really do need to define this. But it isn't defined. What happened later is you get Whitehead and Russell coming along, and they get credit for proving this, given these axioms. But this is actually an implicit axiom. Anyway, no, why are you correcting what I wrote? No. Okay. No, you get that. Okay. What is this doing? This establishes the whole numbers, however you want to describe this, right? So it's the set of these guys. And the reason that this is an implicit axiom is because what we've done, we need this here in order to demonstrate how to generate the names for these new things. Because what we did is we defined this, and then we're magically just supposed to suppose from this that we can produce new names for things. No, you have to actually have to include an example in order for this to properly be extensible. And that wasn't done. So it is actually part of the axiomatic system that 1 + 1 = 2, which is part of the reason that it's bogus that we claim Whitehead and Russell proved that 1 plus 1 is 2. You can't do that. You can't do that from this framework. It's not actually possible. Okay, this establishes the whole numbers. The problem is, when you introduce multiplication, you get problems, right? You get some serious problems, because now you can do things like, well, 6 times 7, right? 6 times 7 gives you, what is it, 9? 1? 3? No, what is it? It's actually 42. But now you can take the inverse of this. Just like with addition, you can take the inverse of it. And the inverse of addition gives you the negatives. The inverse of multiplication gives you fractions. Now you have a problem here, because now this is discrete. So with fractions we get the rationals. The rationals they're not quite continuous, but they're not discrete. Right? Right, so for example, why is 1 a better successor to 0 than 1/2 is, or 1/3, or 1/19, whatever this number is, right? Once you introduce multiplication, you get this, and this introduces problems. It doesn't quite get us to like the level of problem of the continuum hypothesis. Right? We're not quite there yet. But very quickly you're going to be there, because the next thing up from this is to recognize, well, if we extend multiplication to powers, we can take fractional powers, and in which case we get the surds, which are not rational, right? So square root of 2 we can now get, and that's not rational, so now we end up with, it's still at this point not continuous, but we're getting closer to that. We're almost continuous at this point. And then we can recognize things like circles exist, and we can get pi, and we recognize that exponential functions exist, and we can get e, etc. Right? We can just find all of these holes. We can fill the holes in this discontinuous thing. Like, okay, shit, it's continuous. Now it's a problem, and it doesn't work anymore. And this is why multiplication is a problem, and it poses a problem for any arithmetics, any foundational system for math that utilizes Peano arithmetic or Peano axioms, because fundamentally Peano arithmetic contradicts itself. It is not consistent. It introduces paradoxes into its own immediately, which is why you had to have Presburger arithmetic. And that came about a few years before the incompleteness theorems were proven by Kurt-Gödel. And the reason, fundamentally, that it was provable by Kurt-Gödel, I mean, he used a proof by contradiction, but fundamentally what's going on is this is what's breaking it. This is what's breaking it. It's the fact that you are establishing a discrete number system and then just casually saying, oh yeah, we can extend that to be continuous. But then at the same time, you want to uphold the Archimedean property. It just doesn't make any sense. Like, I don't understand how anyone looked at this and was like, yeah, this is good. Especially by the time Presburger arithmetic was put out. Because Presburger arithmetic is so fucking weak. Oh my god, it can barely do anything. Also, it should be the case. It should be the case that multiplication is just iterated addition. So it shouldn't even be possible for a properly arranged system of arithmetic to have addition but not multiplication. And yet here you have Presburger arithmetic, which is modified Peano arithmetic. And the only modification is you removed multiplication. You should not be able to do that. It should be impossible to take out multiplication if you have addition. Because multiplication is iterated addition, right? 2 times 3 equals 0 plus 3 plus 3, or 0 plus 2 plus 2 plus 2. However you want to read that. It's either 2 3s or 3 2s. Okay? I don't care which way you prefer to read that one. It doesn't matter to me. But notice that's iterated addition, right? So here, I'm just going to take that first one to be what it means. Here, what we have is 2 instances of 3 added together. If I can do addition, I can do multiplication. What the fuck? But in Presburger arithmetic, we cannot do multiplication. And the reason that we can't do it is because as soon as we introduce multiplication, it fucks shit up. This is currently accepted. Right? This foundation here. This is what is currently accepted as foundation. This system, which is this simply and obviously broken, is what is accepted right now. Why? Why are we like this?